For this morning's session is David Turton, who will tell us about shockwave in black hole microstate geometries.
You hear it? Okay. Tell me if you're picking it up. Yes. Okay. Very good. Well, I'm very happy to be here. It's thanks for the invitation, and it's a pleasure to be back in person. I'm going to tell you today about a paper I wrote with Badisha Chakrabarti, who is a postdoc at Southampton, and Sami Rawash, who is my PhD student, also at Southampton, who's here in the audience. And this work is all going to be about shockwaves in black hole microstate geometry. So as we've heard very convincingly over the last few days, the time is ripe to further the exploration of the microstructure of black holes. And we've also heard that there's been lots of progress over the last several years in understanding black hole microstates, pure black hole microstates, using smooth horizonless supergravity solutions. We also know that that's unlikely to be the full story. Well, we know it's not the full story. That there are features of black hole microstates that require us to go beyond the approximation provided by smooth supergravity solutions. One way to do that is, of course, to go to stringy features, which will be the focus of some more talks today and tomorrow, but not so much my talk. I'm going to be talking about some, before I do that, we know, I don't need to tell this audience, that black hole microstate geometries and string counterparts are interpreted in the context of the broader proposal, which is that quantum effects are important on the scale of the would-be horizon due to the finite size of the underlying quantum bound state and such that Hawking evaporation is unitary. And if established in general, this would resolve the information paradox. So my talk is not going to directly be about stringy things. I'm going to be in an intermediate regime where I'm going to be using supergravity fields, but relaxing the requirement of smoothness. And I'll do that by introducing shockwaves. These describe the back reaction of high-energy massless particles in such a way that we'll have a physical singularity in the supergravity fields, but one that we have relative control over. So you probably all know that gravitational solutions involving shockwaves have attracted lots of interest in recent years in the context of black hole physics and quantum chaos in holography. In particular, shockwave collisions on black backgrounds probe the absorptive nature of the black hole horizon and the sensitivity and this has provided insight into the chaotic behavior of holographic CFTs, in particular through out-of-time ordered correlators. Separately, and before that, shockwaves appeared around 20 years ago in the study of two-charged black hole microstates, as I'll review in some detail shortly. And in these solutions, we have a shockwave deep inside the core of the solution, which is describing the back reaction of a smeared beam of massless particles. And the supergravity fields are not going to resolve the details of these particles, but we'll see that their overall effect through their energy on the back reaction of the solution. And these solutions are relevant to investigation of dynamics and scrambling of perturbed microstate geometries. So in particular, let's take a BPS black hole microstate geometry and imagine perturbing it to becoming slightly non-BPS and ask what's the resulting dynamics, what's the state which it evolves to. Well, it will naturally relax back to some BPS configuration, and we can ask, is it going to be the same configuration we started with or some other configuration? There was an argument presented a few years ago that if you think about a massive probe particle coupled to supergravity fields, that it will naturally radiate soft radiation and gradually minimize its energy by falling deeper and deeper into the core of the solution. And it will minimize its energy by approaching a null geodesic, which is deep in the core at an infinite redshift surface. So there were some questions maybe yesterday or the day before about how deep the redshift can be in some of these throats. Well, depending on the asymptotics, if we work with flat asymptotics, there are surfaces of infinite redshift as viewed from asymptotic infinity. And so there, the particle can approach this null geodesic, where locally it will have a very large energy to the local blue shift. And that means that we should need to take back reaction into account. And in terms of a classical analysis, this was described as a potential nonlinear classical instability. For two-charge microstates, so this was largely in the case of two-charge, but also for three-charge. Specifically for the two-charge microstates, Andrea and Don Morel from Ben Mitchell modeled this process using some previously constructed solutions involving shockwaves to try and describe this back reaction as part of the perturbation process. And they interpret it as an evolution from less typical to more typical microstates. So that's broadly correct, but I think some details or some important facts were not appreciated, which were clarified in later work. If you take a holographic perspective, then it's not particularly accurate to call this an instability. At the quantum level, you have, on the two-charge phase space, a flat moduli space, which if you perturb by some finite energy, the system can explore nearby phase space, but it's not the case that this is a runaway to arbitrarily far, to arbitrarily typical microstates if you have a limited energy supplied by the perturbation. So this is more accurately described as scrambling. The system, if you give it a little bit of energy, wants to scramble into nearby microstates, which are going to be more typical than what you started with, but how typical you can become depends on the energy that you supply. Relatedly, if you study more stringy probes, then we get tidal effects that lead to stringy scrambling physics. This gives us, as was discussed yesterday, very interesting absorptive features of black hole microstate geometries with long throats. And Ben and collaborators have also studied out-of-time ordered correlators in extremal BTZ type geometries, which exhibit a slower scrambling than far from extremal solutions, but one which one can study quantitatively. So all of these things, all of these developments motivate the study of more general solutions involving shockwaves, more general microstate solutions that have shockwaves in their cores. And in this talk, I will present the first family of asymptotically flat, three-charge microstate solutions that contain shockwaves in their cores. I'll also identify a family of holographically dual CFT states that we propose are dual, and I'll report that they pass a set of tests, a set of checks, including a precision holographic test. Any questions on the broad outline before I put a bit more flesh on this story? Okay, so the route I'm going to take is a very brief review, just so we're all on the same page, of the Eichelberg-Sechsel shockwave and its generalization to global ADS times S3. I'll then review shockwaves in two-charge black hole microstate geometries, and then proceed to our construction of the new three-charge solutions and their holographic description. So this original Eichelberg-Sechsel shockwave arose as the back reaction of a massless point particle in 3+1 GR. You can find the solution either by solving the linearized Einstein equations or making an infinite boost of the Schwarzschild solution. We find a gravitational field which is non-vanishing only on a plane containing the particle in orthogonal direction of motion, and we have some delta function which controls the motion of the particle. Okay, so this is a well-known solution which has a delta function curvature singularity on this plane for a non-trivial back reaction. Now we can smear this. So this was explicitly time dependent because we have the trajectory of the particle as it goes along its null geodesic. We can smear the shockwave to obtain a time-independent metric. So if we simply smear along the direction of motion, we get the back reaction of a null ray or a beam of particles traveling in that direction. And so this was all so far in 3+1 dimensional space-time, but we can of course do the same, if I get the mouse out of the way, in 5+1. So in 5+1, the corresponding feature, the non-trivial function which appears here is the appropriate harmonic function in the four transverse spatial directions to the particle. That's what it is, I think.
It's 5 plus 1.
5 plus 1. Yeah. Okay, so you can take that solution in flat. Okay, you can repeat it. The question was the power correct here? And the answer is yes, because we're in 5 plus 1. Okay. So, okay, we can. Q is the overall energy of the shockwave. Yeah, it controls the overall energy. So it's the strength of the shockwave. So the more energy the particle has, the higher the Q. Yeah, thanks. That's going to be. So this quantity Q is going to play a role throughout the whole talk. Okay, so one can construct a similar solution in global ADS 3 times S3. This was constructed by Lune and Mathur in 2002, essentially by brute force, tour de force calculation. And we have L here, capital L is the radius of ADS. And we have on the first line here, essentially the global ADS 3 times S3 solution without the shockwave. And this whole second line here in the metric is proportional to Q. So all of this second line is the back reaction of the shockwave. And since the shockwave is traveling along psi. Yeah, so it's traveling along psi at r equals 0 in these. No, it's one of the Cartan. You see here, this is the metric on the S3 up here. It's one of the Cartan U1s. Yeah, it's not the hop fiber, it's one of the Cartan U1s. So in this conventions, the shockwave is at r equals 0 and traveling along psi. Okay, so, and because the background has a two-form tensor potential before you deform, we also get some appropriate deformation of the Ramon Ramon two-form potential, proportional again to the strength of the shockwave. So this solution is going to be one of the sort of seed solutions I'm going to use for the construction. So in particular, yeah, question? In a moment, this will be an evanescent ergo surface. At the moment, it's not, because I'm in the global NSNS vacuum where this is just global ADS 3 times S3. So I don't have any infinite asymptotically flat direction with respect to refer to that. But on the next slide, it will become an evanescent ergo surface. Okay, so how do we do that? Well, we perform space-time spectral flow to map this global ADS 3 times S3 solution into maximally rotating circular supertube Ramon ground state. And when we do that, and when we add back in the flat asymptotics, the location of the shockwave is precisely on the evanescent ergo surface, and that's as it should be because this is some other Ramon ground state, so the shockwave has come at 0 cost of energy. Good, so what does the solution look like? Well, asymptotically, it's quite similar to the original two-charge maximally rotating circular supertube, but with reduced angular momentum. And that's not surprising because we started with had the maximal angular momentum, and we've deformed it. Deep in the core, of course, the solution differs from what was just global ADS 3 times S3, such that locally we have exactly this kind of singularity we see here. So when these functions go to 0, when r is 0 and theta is pi by 2, this is our physical shockwave singularity.
Make the solution by just not putting Q1, Q5 over RY squared equal to A squared. Is it the same solution as not satisfying the supertube smoothness relation, or is it something a bit more clever?
It's very closely related to that. If you do that, but you're very careful about which quantities you're holding fixed, you will land on this solution. But it's a delicate procedure. You have to be very careful. So you're going to break the smoothness requirement, but you have to do that in such a way that you want to hold Q1 fixed, Q5 fixed, R1 fixed, and it's A, which controls the angular momentum, which is going to reduce, and therefore break the smoothness requirement. So if you do that sufficiently carefully, in this instance, you can make this microphone.
This
understanding, you keep saying the things that r equals 0 and theta equals pi by 2. Is it, but looks like what you've written, it's r equals 0 and theta equals 0, or am I misunderstanding?
It's entirely possible that Luna and Mathur had opposite conventions to us. So let me check. Okay, in this conventions, indeed, it's theta equals 0. Yeah, I think that's going to change on later slides, though. So let's not cement that in our minds for the rest of the talk. I wanted to not change their convention. So this is their metric in their conventions. So at the moment, it's at theta equals 0. I think this is BPS. It's 2 charge Ramon Ramon ground state, 4, 4 BPS. Half BPS solution. Thanks. Any more questions? Okay, so as I said, deep in the core, the solution contains a Shockwave singularity. And we can also obtain the solution by coarse graining over a set of profile functions, 2-charge profile functions, which I'll say more about once I've introduced that concept for those who are not experts in this story. So I should say, as I go along, I try to make this talk as accessible as possible to those who are non-experts. Of course, there will be some slides in there for the experts, but please interrupt me if anything is not clear. Okay, so just a quick review of the 2-charge system for those who are not experts. Let's first consider a multi-wound fundamental string carrying winding and momentum. This is perhaps the simplest system in string theory with some exponential degeneracy of microscopic states, which is nice and compact, and it corresponds to a small black hole. If we give the string a classical profile, then it sources a good supergravity background. And these classical profiles correspond to coherent states in the Fock space of the string. These solutions don't have any horizons. There is a physical source at the location of the string. And the string has to carry its momentum in transverse vibrations. It's a fundamental string. So the system occupies a non-trivial size. The F1P configuration is usual to D1, D5. And in the D1, D5, excuse me, in the D1, D5 duality frame, the configurations are everywhere smooth after some smearing has happened along the way. And the D1, D5 is nice and well studied because, in large part, because we can study precision holography. So to be fully concrete, we're going to work in type 2b. I'm going to take a T4 compactification for concreteness, and we'll wrap N1D1 branes on the S1, N5D5 branes on the S1 times T4, and NP units of momentum along the S1 when we have 3 charges. And for states which have geometrical descriptions, they'll have supergravity charges proportional to these integer numbers of branes according to this. We'll be interested in taking a decoupling limit in which the solutions become asymptotically ADS3 times S3 times T4. And we'll go back and forth between the flat asymptotics and the ADS asymptotics, depending on whether we're doing holography or not. When we do holography, let me review, as was nicely reviewed a bit in Sean's talk yesterday, or the day before. The wall volume gauge theory on the D1, D5 bound state flows in the infrared to a 4,4 superconformal field theory. The relevant part of the theory is its Higgs branch, which is a deformation of the symmetric product orbifold on a target space T4 to the power n modulo the symmetric group Sn, where n is n1 and 5. It is a weak strong duality, as is usual in holography, but we can compare protected quantities between gravity and the orbifold CFT, and we will use that when we do our precision holographic tests. Okay, so having introduced a bit of our background, let's talk about these supertube profile functions for the solutions I've discussed so far. This first one on the left is the maximally rotating solution that I mentioned at the start. So it's a profile of a string which transcribes one single helix in some appropriate covering space of the S1 on which the branes are wrapped. The physical S1 is some small fraction of this direction here. So you should think of this as building up lots of winding charge as it traverses a ring in space-time. And so this is a big fat thing which doesn't look much like a black hole. But if we get the trajectory, to turn on itself multiple times, the whole configuration becomes more and more compact. So we get closer to a black hole or a small black ring type configuration as we crank up the parameter k. These are very special configurations. They have lots of symmetry, and they admit explicit study. A particular interesting family of solutions that I'm interested in today arise from these circular supertubes from an operation known as spectral flow, space-time spectral flow. So I should say before I go on that this parameter k that I've introduced here in the profile function controls how many times this two-charge supertube winds on top of itself. And when the solution back reacts, we get a zk orbifold singularity inside the core. So locally near the core of the solution, it's like a zk orbifold of global ADS3 times S3. So these zk orbifolded solutions are particularly interesting for what I'm going to do next. By using space-time spectral flow, we can generate solutions with this as seed, which are 3 charges and either BPS or non-BPS. And in this talk, I'm going to focus on the supersymmetric states within this family. So these solutions were made back in 0405 by Lunin, GMS, and JMART. And then later on, in a couple of papers, we understood that there's actually a larger set of states that can be studied with simple generalizations of these solutions, which involve fractional space-time spectral flow. And that's important physically, as I'll review in a moment. But what you should keep in mind is that when k is bigger than 1, we have this fractional space-time spectral flow with a fractional parameter nu, which is equal to s over k, and that'll appear throughout the talk. And if we have the non-supersymmetric version, there's also a right-moving parameter s bar, and Nico will talk about that in the next talk. So just to get a sense of the conserved charges of these backgrounds, so far there's no shockwave yet in the 3-charge story. So where do these states lie in the phase space of angular momentum J3, the left angular momentum, and the momentum charge NP? Well, the integer spectral flow states all lie on these straight lines. So, well, firstly, these are 2-charge states down here. They have momentum charge equal to 0. And the orbifold parameter k controls the angular momentum, so the maximal rotation is k equals 1. And all the others, each successive one is maximal amount divided by k. So here is k equals 2, 3, and so on. Spectral flow is an operation which translates you along orbits which follow this parabola, which is inscribed here, effectively. And the integer spectral flow states are all lying on these extreme lines, which are the bound of the allowed charges of the CFT. The important and interesting thing about the fractional spectral flow states is that they lie in the interior here, relatively close to this parabola on the scale of this plot. So all of them are outside the parabola, and the parabola demarcates the region inside here where we have BMPV black holes, single-centered. Outside the parabola, there's a more complicated phase space, which involves black rings and supertubes, and we don't need the details really for today. But this is just to emphasize the difference between what we can get with integer spectral flow and fractional spectral flow. Any questions on, yeah?
Usually on the parabola you have Neber-Schwarz states, and on the lines you have Raman states. But this is fractional spectral flow, so the notion is not...
So when we have, it's a good question. So these are all going to be Raman states. Once you're careful about what you mean by Ramond and NS when the parameter k is switched on. So when the parameter k is switched on, the physical notion of Ramond versus NS is defined in a k-fold covering space. And there it will depend on whether this parameter s is integer or half integer. And in this talk, I'm always going to take s to be an integer. So these are all Ramond states. So these are Ramond ground states, and these anything with non-zero NP is an excited Ramond state. Any more questions on Guillaume? Microphone. Good. Thanks for the question. Okay, so great. That was all without shockwaves. Now, what does it look like when we do a shockwave? Well, I said we were going to take a coarse-grained limit of profiles. So let's go back to two-charge for a moment, and let's understand properly the two-charge supertube plus a shockwave. Well, we can take a coarse-grained limit of profiles which have some component which was the original shockwave. This, let's take, for instance, the k equals 1 maximally rotating profile. And we add in some component of higher Fourier harmonic according to some high energy particle. So if we add that directly, we get something that wiggles like this solution here. This is not a shockwave. This would be a smooth solution because providing these wiggles of the profile are bigger than the string scale, can actually write down the smooth supergravity two-charge solution there using the general two-charge dictionary. So the shockwave is not this. It's something different, and Lund and Mathur got this by coarse-graining this kind of profile here, which, if you look carefully, there's a segment at the end which is a straight line up, which is not a physical profile, it's an auxiliary profile. But what they did was to have some component here which is the k equals 1, some other component here which is physically, not a physical profile, but it goes directly up. And then they made a process in which this straight line segment was chopped into very small pieces and smeared all along the profile. So let me just sketch what that means. Let me try my best 3D rendering. Okay. So what we're doing here is we're coming around here one bit, and we're going to have a straight line segment, come around a bit further, go up a little bit, come around a bit further, go directly up a bit more, and keep going around. Okay. Modulo my artistic talents, hopefully you get the idea. Okay, so we break up this, this little segment of constant profile into many small chunks, and then we smear the whole thing. So what's the effect of this? Well, when we saw these original simple profiles, hopefully you got a sense that the higher the harmonic, the more compact the extent. I mean, it's here, so the Fourier coefficient is divided by k for higher k's. So each time we add a component of higher Fourier harmonic, this takes away some of the ability of this k equals 1 part to expand. So the whole thing has shrunk a bit when we've added this, this thing. So I tried to depict it. This whole thing is already a bit more compact than it would have been with just k equals 1. And the same thing's happened here after we've smeared. So we've ended up with something after smearing which, if we use a different color, has gone back to being circularly symmetric, but it's smaller than it would be if it were to be smooth. Okay, so we've obtained a solution by smearing which has again plenty of symmetry, but it's no longer smooth. It's singular because it's more compact than it should be. Is it more or less clear, or any questions on the Lund and Mathur shockwave? Okay, so when you do that, so in our construction, we're going to do something similar. So, but first, we're going to take Lund and Mathur's k equals 1 shockwave solution, and we're going to introduce the k orbifolding. So we're going to have this supertube which winds on top of itself with a shockwave and with the zk orbifold. And so that looks very similar to what we had before, But now we have, on the first line, K orbifolded global ADS3 times S3. And so the appropriate Shockwave thing has powers of K everywhere. So this is the supertube plus Shockwave with ZK. Try and get this thing out of the way. With a ZK orbifold, yeah. It's easier to see. I haven't written it for you, but it's easier to see at the level of the harmonic function decomposition. If you write the HKA, then it's exactly what you would do. You're averaging over this at the level of the the two charge integrals, exactly the way you know how to compute a profile. So you would have when you take this thing, you have I'll show you the profile in a few slides time, actually. You have two separate segments that would go into your two charge integrals. And then by doing just the obvious kind of smearing inside the integration, then you get the solution. Okay, so this is our ZK orbifolded two charge supertube with Shockwave. And now building on this with a couple of fairly straightforward solution generating techniques, we're going to make three charge BPS solutions with Shockwaves. So the first is, because we now have the parameter K in the game, we can make a fractional spectral flow of these ADS solutions. So for the first step, I'm fully in ADS3 times S3 decoupling. So we take this two charge solution and make a fractional spectral flow. This gives us solutions with three charges by a relatively simple large coordinate transformation that depends on the parameters S and K. It mixes the time and Y coordinates with the S3 angles phi and psi. So when we do that, we obtain a new solution which is asymptotically ADS3. It has three charges and a Shockwave. So that was fairly straightforward. The bit that requires a little bit more work is to extend this solution to an asymptotically flat solution. But that's also not too bad, because you can take this solution and decompose it into the harmonic functions of the Boehner-Warner formalism. So it requires some work, but you can do it. And so by this, we get the harmonic function decomposition of three charge solutions with Shockwaves. And once you've done that, you can trivially add back the ones in the harmonic functions. And this gets you new asymptotically flat three charge solutions. It's easy to say, but the answer you get at the end of the day is a bit of a mess, as any of you who have worked with these kind of solutions would imagine. So instead of presenting you the whole big ugly metric that would fill the slide, let me just show you, for the experts, the charges of the multi-center description of the configuration. So we have two centers, which is the same as the spectral flowed three charge BPS supertubes without Shockwaves. And compared to the seed solutions, in the same way here that the whole solution shrunk down to a smaller size, we have the two center configuration, which has also shrunk down by some amount. And that's controlled by this parameter Xi, which is defined to be 1 minus Q, and where Q is between 0 and 1, but strictly less than 1. So just to calibrate everything, now that we're switching from Q to Z primarily, Xi equals 1 is going to be the limit where the Shockwave is turned off, and we go back to the original separation of the centers. And as Xi approaches 0, that's the limit where the Shockwave is dominating the background. And you can't take it all the way to 0 within the approximation we study, but that's the range of Xi. And so we'll work with rescaled distances R plus minus, which will be rescaled by Xi. So when we do this, we have two centers, but they're not both smooth centers. They shouldn't be.
Sorry. When you say it dominates the background, what exactly do you mean?
You'll see it in a, will you see it? You'll see it a little bit when I show you the plot of charges. But basically, these solutions sort of rely on the Shockwave and the part which is not the Shockwave, both sort of contributing at order 1 to the back reaction. So this parameter Q is sort of like the component of the overall gravitational solution, which is corresponding to the shockwave. So it's natural that Q is sort of like a smaller than one thing if you're just adding a small shockwave. But once you have the back reaction, you can crank up Q until the solution develops a pathology. And if you crank up Q to be order 1 but not particularly small, then you have a solution which has a big, nasty shockwave with lots of energy down inside the throat. And the overall configuration has gone quite a lot smaller. But there's a limit. You can't take it all the way to be dominating everything, because that would invalidate our approximation and you would develop a singularity. And the solution in that limit goes towards a small black hole. But you'll see that from the charges in a moment.
Normally, if I was expecting you to shrink the two centers together, I'd expect closed time-like curves to develop. So
yeah.
What are you doing to kill? Are you just cranking up a charge somewhere else to kill off the closed time-like curves and rebalance the system?
Wait for a minute and I'll tell you about closed time-like curves. It'll all be fine. Okay. Because of our solution generating technique is the short answer, but let me give you a more complete answer in just a moment. How am I doing for time? Good, so we have two centers. They've been scaled down to a more compact configuration. One center is smooth, but the other center is singular. And that's the correct physics because we have a singular shock wave at the location of one of the centers. So it's correct that one should be singular. And these are the charges of the centers. And in this language, the deformation is relatively simple, I would say, if you're familiar with these things. So if you just quickly scan and look for where Xi appears, all of these charges, which are the charges of the harmonic functions V, K, L, and M in the usual language, Xi appears nowhere. All of these charges are still the same as they were in the original solution. They only depend on S, K, and charges. Here is where Xi appears. It deforms the local momentum, the sort of L3 harmonic function near the singular center, and also the angular momentum M charge near the singular center. And when Xi equals 1, you get a nice perfect square here, and everything goes back to being smooth. But for general Xi, this is how the solution goes singular. Question from Josef over there. Who has the microphone?
So, you get oftentimes when you mess up with the center with the harmonic function. Oftentimes when you mess up with the harmonic function coefficients, you end up getting a small black hole at one location or a small black hole at the other location. And normally you have 16 supercharge on one center if it's smooth, you have 8 supercharge if it's semi-smooth, and then you have 4 supercharge when you have a black hole. How many supercharges do you have here at the center? Can you figure out?
It's a good question. We took a little look at it, but I don't think we had a conclusive.
It's a cheap way to compute the quartic invariant, and then if the quartic invariant is non-zero, then you have a black hole. If the derivatives of the quartic invariant are non-zero, then it's a supercharged solution. And there's some paper by Kalosh which has a very nice, clean way to understand what you have.
Just before we put the paper out, we became aware of this and we took a little pass, but I don't think we conclusively decided for ourselves how many. This for sure is less than. So this is the usual 16 subcharge smooth thing. We didn't come to a conclusion on how many the singular center charge, but it's something we can compute for sure.
But the supertube only has, still has the same D3, Q1, Q2, and M, right? So you're just messing up with the M from the supertube perspective.
L3 and M.
L3 and M, but in the supertube you're just messing up with when you have a supertube before the spectral flow.
When S goes to 0, yeah. So you can see it here. So when S goes to 0, this one is killed. So it's purely the M.
Okay, so then you probably have 8 supercharges then, because it's like the same as putting one D0 on top of the supertube. So the supertube has 16 and you're putting a D0. So you probably have 8 supercharges.
In the 2-charge limit for sure, for the 3-charge, okay. It's a small calculation, so but it's checkable for sure.
Thanks.
Okay, so to come back to Nick's question about CTCs, so when we realized this was decomposable in 2-charge, we thought, okay, we can check your sufficient condition for absence of CTCs. That's not satisfied automatically, so we had to check it by hand. But in the decoupling limit, you can check it fully analytically, complete the squares, the usual thing, beautiful, no CTCs, as long as you don't crank the Q parameter all the way to the extreme value of 1 when it becomes a small black hole and then the CTC check fails. But we're going to stay away from that singular limit, and if we do that, everything's nice and beautiful, and for the asymptotically flat solutions, we checked it numerically as one usually does, and everything seemed totally fine. In supergravity, you can also compute the conserved charges. So similar to the supertube, so we've shrunk everything, and so angular momenta have reduced. An interesting thing is also that when we do this procedure, the QP charge also goes down. So when C is less than 1, we have a smaller QP charge than we started with, provided that S was positive. If S is negative, it's a slightly more delicate story, but I'll show you in pictures because it's easier in pictures. Okay, before I go to holography and that, any more questions on the gravity side?
Just,
yeah.
You can presumably generalize this by checking. You don't have to use the fractional spectral flow. You can just add momentum at will and generalize this construction, or is it?
I certainly hope so. Yeah. So I think this is ripe for plenty of further generalization on the supergravity side. Yeah. So that would get us inside the parabola if we could do it, for instance, with superstratum type technology. Yeah, I'm very optimistic about that direction. Okay, so again, yeah.
So if you check locally the singularity of the shockwave, you can really match the original singularity of the shockwave in the simple background, right?
Yeah.
I guess
Yeah, absolutely. Essentially by construction, because we made it by a large coordinate transformation of that two-charge solution. So when you core and you choose appropriate coordinates, you see it's identically the same shockwave. So I think there's no doubt that this is a physical shockwave singularity that we have there in the core. Okay, good. So again, just brief intro for those who are less expert on these matters. In our orbifold CFT, we have n copies of a C equals 6 T4 sigma model. On each copy, we have 4 bosons, 4 chiral and 4 antichiral fermions. And we have twist operators which generate twisted sectors, just as Sean was describing in his talk. And the lowest dimension twist operator generates a sort of monodromy, which involves a minus sign at the final step, so that the fermions in the covering space are in the NS sector. And then one can make Ramon sector operators with twist fields as one needs. So this gives us various sort of components of the overall CFT, which are often referred to as strands. Strands of length k means I have a twist k operator which has combined k copies of the original CFT into one k-wound sort of chunk of CFT. In each twist k sector, we have 5 T4 invariant Ramon-Ramon ground states, which we label by their charges under SU2 left times SU2 right, the R charges, the R symmetries of the CFT. And these can take values plus or minus a half, there's 4 states like that, or a neutral state 0, 0. And you can obtain these spectral flow, CFT spectral flow of the antichiral primaries in the NS and S sector. And when we talk about states which are dual to macroscopic supergravity backgrounds in the bulk, we have in mind some coherent state where we have some particular coherent sum over states which have large numbers of these twist operators, some in a particular way, such that we should really always be talking about the average values of the strands which appear in the coherent sum. In the remainder of the talk, I'll try and simplify the presentation by assuming that this coherent sum is there in the background, but I'll just show you sort of the main component of the sum. So how we develop our proposal is to first refine and make more precise the previous proposal for the holographic dual of the 2-charge solutions with shockwaves. Lin and Mathur had a sketch of that in their paper, which we were able to improve upon. And we can combine this with a precision holographic test. And having done that, so all the hard work goes into nailing down the 2-charge description to the level of precision we can probe. Once we've done that, everything will follow from holographic CFT fractional spectral flow on the CFT side. So recall I had this profile before the smearing for the 2-charge solution with shockwave. We have a dictionary for the holographic CFT duals of such configurations, at least those for which the profile was physical, so that it was really, without this straight line segment, we know what to write down. For each Fourier harmonic, there's an appropriate component of twisted Riemann ground state. We have to, sort of relax or generalize that a little bit to develop, to be able to describe a family of CFT states which are compatible with this straight line segment. So let's do it in a couple of passes. This is a bit of a long slide, but let me take you through the steps. So first pass is we're going to have some component of twist K ground state corresponding to the main sweep of this profile. And then we're going to have some component which involves longer strands, which are dual to the shock wave. We won't be able to resolve the details of that, so we'll have to just write down some general family of states which are compatible. And so here in the CFT, we have this first component, which is the original K1 supertube, and then some family of longer strands whose details we don't resolve. I need to get this thing out of the way. Okay, so for concreteness, we'll label them by their spins, epsilon and epsilon bar, to be these 5 Riemann ground states. So this, you should think of all this component as just some other longer 2-charge Riemann ground state strands with some certain conditions, which is that their windings should be multiples of K. That's important for what follows. Their windings should be appropriately large in a way that one can make precise. There's the overall strand budget of the CFT, which is this number of strands in the whole thing is equal to N1N5.
Don't those other strands develop a profile in the other R2?
Wait for a moment. And because we don't want the other strands to develop a profile, we have to put more conditions. That's this last thing here. So as a first pass, one necessary condition is that these, where's my mouse? What we don't want is that we don't want any of these long strands to have a degeneracy of order n. If they had a winding of order 1 and a degeneracy of order n, we would see it explicitly in the profile and we would have this spirally helix, okay? That would be one possible smooth resolution of the shockwave, but it's not the shockwave itself, so we have to exclude states for which we would see the wiggles. So absence of visible wiggles, if you like, imposes at least this, this necessary condition that the degeneracy should scale as some power of n which is less than 1, strictly less than 1. We'll be able to do better. We'll have to do better than that, but just as a first pass, we don't want to see the wiggles. And for simplicity of the discussion, I'm going to assume that K, Q, and Xi are all order 1, which is the natural regime. And the rest of the parameters due to the long strands are not fixed, and we don't have information about them. They're not resolved by the shockwave. And that's just that, as I said, the total energy of the shock is fixed, not the detail of the individual pointer. Okay, so to improve on this, we do some precision holography. We compute a heavy, heavy light 3-point function, which is protected between gravity and the Oberfold CFT. So it's the expectation of a light operator in this heavy background. And light heavy means that the light operator has dimension order 1, and the heavy operator has dimension of order the central charge. So it's protected, so we can compare its value, and this gives us more information on the CFT dual state. And the particular operator we're interested in is a scalar chiral primary of dimension 2, whose precision holographic dictionary was recently derived, also by Sami, who was on all these papers, together with Stefano Giusto and myself in these 2 papers you see there. This is a mix of single trace and double trace operators, and this is a whole story by itself, which I already talked about in previous black hole microstructure conferences, so I won't go into the details of that. But what we need for today is that a particular component of this, the 0, 0 component, is a quantity which has a non-trivial 0 in the sense that when you expand the dual fluctuation in the supergravity, which is some scalar fluctuation, it vanishes in the shockwave solutions. And in these CFT states, therefore also require 0, but we have quite a non-trivial cancellation to arrange between three components here which have non-zero vevs. So the sigma 3, omega, and jj bar all have non-zero vevs, but their precise combination in this operator has to have a zero expectation value at leading order in large N. So when you compute that, you get a more refined constraint on the CFT state, which is that the sum of the degeneracies of the long strands has to scale with large N as some power strictly less than 1. And that maybe looks like it came from nowhere, but we'll see that it has important implications. And this is our precision holography input. And this is, by the way, much more refined than you would get if you were comparing conserved charges directly without this information. But when you do then further match the conserved charges, then we get our precise proposal, more refined proposal, which is that two conditions come out which were to be expected, but we didn't assume them going at the very start, which is the parameter Q and Xi directly control what's called the strand budget of the original supertube strands and the Shockwave strands. So the total number of strands k times n naught is Xi times n, so Xi is the fraction of strand budget in the original supertube, and Q is the fraction of the strand budget. So that was to be expected from the profile, but we derived it directly. And then we have this extra condition I just showed you. So to the level we can probe with precision holography, this is a large family of CFT states which are compatible with the supertube, two-charge supertube with Shockwave. Having done that, yeah, go ahead, Andrea. Microphone. Oops.
Is psi an integer?
Is Xi? No, no. Xi is a real number.
Okay, but k and 0 and n are.
But we're in large n limits. So.
Okay, so you mean it's fine.
Yeah, yeah. So yeah. In the supergravity, we treat Xi as a real number. Of course, when you want to do this whole thing, then we should take rational approximation to your favorite real number, such that you can solve the appropriately. So yeah. But we're in the large n limit. So these conditions, we're not worrying too much about this particular Diophantine story. We will worry about integer quantization in just a moment. Good, but thanks for the question. So now we're going to perform holographic CFT fractional spectral flow on this more precise proposal for the two-charge states to get our three-charge states. For those who are not so familiar with this, all we're basically doing is taking each of the ground states, whether they be the shorter strings or the longer strings, and we're filling Fermi C of excitation to some appropriate filling level. And that filling level is important. So we are doing the full spectral flow of the full CFT with some fractional parameter nu. And on the original strands of length k, that's some fraction s over k. But for the long strings, that's some different value s, such that si over ki is equal to r nu. So that means that the longer the strand, the more fermions you fill on top of it, such that the overall fractional spectral flow is controlled by a single parameter nu. And okay, so that gives us states like this, where we have a ground state, we have a bunch of fermions filling up two Fermi Cs, and we'll denote all these excited states with a single extra s parameter down on the state there. Okay, so performing that operation on our two-charge CFT states, we get our proposal for the three-charge solutions with Shockwaves, where we have some of these fractionally spectral flowed supertube states with parameter s and k, and then some longer strands whose details we don't fully resolve, but all of which carry momentum and angular momentum according to what's generated by a spectral flow. And the conditions are the same as we had before, so the ki are long and multiples of k. The Xi and Q still control the relative fractional strand budget, and the overall holographic CFT precision holography constraint is the same as it was before. Subject to one important condition, which is we can't do this for free because there's an additional condition in the holographic CFT that the momentum on each strand must be an integer. And so not every value is allowed here. We have to one extra constraint. And it turns out that that's a non-trivial constraint. And this is why we do have to worry a little bit about integer Diophantine number theory. The condition that the momentum on each strand be an integer is different on each strand. So we have some original thing that was inherited from the background, which gave us some allowed values of S and K, which were compatible with the background carrying an allowed momentum. And now we have long strands, and we have to ensure that also these values, or at least we want to satisfy ourselves that there's plenty of solutions to long strands carrying allowed momentum. And so that's something you have to check, and you can show with a little bit of elementary number theory, some application of Bézout's identity, basically, that there is an infinite family of long strand lengths Ki such that you can satisfy this constraint for any epsilon I. Emil has a question. Where's the microphone?
But I thought S over K had to equal SI over K. Did I read that correctly on the previous
You did read
slide?
that correctly. So the perspective here is that we are choosing from the start S and K, and so nu is fixed. Okay. What's not yet fixed are the values of Ki, and so we want to ask the question, which are the allowed values of Ki, such that when we choose them, this will fix Si, because nu is fixed, such that all these quantities, such that this quantity here is also an integer.
But epsilon I is like plus minus
Plus
1.
minus 1. So there are 3 different conditions to check, depending on whether epsilon is plus minus 1. So plus minus 1 or 0. So three options for epsilon. And what we want to satisfy ourselves is that we want to be working at large n. So we want to make sure that there's an infinite family of allowed Ki stretching to arbitrarily large values of integers, such that there are solutions to this no matter how large we want to go. And so because we're not resolving the precise Ki, we just want to make sure there's plenty of allowed space of states there in the integers, and we find yes.
I guess you always have solutions when S is a multiple of K.
When S is a multiple of K, that's integer spectral flow, so that's always the easy case. So yes, that's fine. But when you have fractional spectral flow, you have a short little thing to check with some number theory. But in each case so you have to separately check the cases for epsilon equals plus 1, 0, and minus 1, but it works.
So if you imagine not doing something more general with momentum, then you would just have some quantization of momentum condition on each strand. It would be easier to satisfy this probably.
You mean if you allow your momentum carriers to have different values? Yeah, so if you had a separate parameter, indeed. So in the superstratum, you have a separate parameter for how much momentum you add. So you wouldn't have to be as careful as this because you have a separate parameter. You say, if I land on something with not the correct momentum, I'll just excite it until it hits an allowed value, and that's my solution. Here, things are more constrained, so we do have to check. OK, good. I'm almost done. Let me show you what happens to the solutions. So the dots here, I've zoomed in a little bit to the plot I showed you of the spectral fluid supertubes. And what I'm plotting here are both dots and crosses. So let's take, say, something out here, which is an integer spectral fluid solution. So the dot is the solution without the shockwave. The cross is the solution with the shockwave with some particular strength, Q equals 0.2, just chosen for the purpose of plotting. And what you should think is that there's a family of solutions with shockwaves that interpolates between this extreme, more atypical state here, all the way towards the BMPV parabola, but never crossing over. It's always staying slightly outside the parabola. That's our limit. So in the limit, these solutions approach the BMPV parabola, they approach the small black hole, but they never quite get there. So we're always slightly outside the parabola. And two things are interesting, worth highlighting here, is that I mentioned that the fractionally spectral flowed states were already pretty interesting because they were already quite close to the parabola. So of course those guys go even closer to the state. So the colors match. So when you look, you have to look a bit closely to see what matches what, but here's an orangey one dot where the cross is quite close, so it's already quite close, and it's going closer. Interesting feature is that the shockwave is, on this side of the diagram, is reducing J3 and reducing momentum in terms of conserved charges. On this side of the diagram, it's reducing J3, but that means it's increasing the absolute value of J3, and it's actually increasing the momentum. So the things here are flowing upwards in QP, the things here are flowing downwards in QP, all along their appropriate trajectory. But everything is BPS, so when we add momentum or subtract momentum, the energy shifts in exactly the same correlated way to get BPS 3-charge solutions. Okay, so if there are no questions about the pretty picture, I'm wrapping up, so go ahead.
So what happens when you increase the strength of the shockwave? So where do I mean, can you show somehow like, orbits or?
Yeah, so you should extrapolate this towards the BMPV parabola from each thing. The precise trajectory depends on those conserved charges, which are multiple slides ago, but I think I can get back there. So these are the formulae. So J3 is decreasing linearly with Xi. QP is this combination, this last term inside the ADM mass. So that's also linear in Xi, the term which is chronoling, but not going all the way, some inhomogeneous linear function. So then on this line, you're just following linear trajectories. So you can just extrapolate each dot and cross that have the same color as each other linearly until it hits the parabola. And so, of course, it doesn't quite get there, but that's our interpolation between different microstates.
Sorry, just one more question. Does it go from, like, for example, do lines go from one point to the other? Like,
yeah, so continuously what we're talking about is this cross would approach linearly this dot as q goes to 0, and it would approach the parabola as q goes towards 1.
At a random point on the parabola, not
at the precise point that what you get when you extrapolate these 2 points to make a line.
So these are all zero horizon area, or are they finite horizon area?
On the curve, on the BMPV, it's 0 horizon area.
Okay. There are no horizons on any of these things then, right?
No.
Okay.
These are all horizonless solutions.
If you have horizons, then you get a count of the averaging over the states you're going to do. If you did the superstratum version of this and you've got a fat horizon, that should give you some count of the coarse graining you've done.
Yeah, so there is a toy version of that you could already do here. You could count amongst this family of CFT states that I've proposed. There's some degeneracy there, which are all equally not resolved by the shockwave. And you could count an entropy associated to that, which would be sub-black hole-like, presumably, or it might be similar to what you get in a... Wait for the plane to pass. It looks also quite similar to what you get in a zero-size limit of a black ring. And these are a bit closer to that in spirit. So if there's a matching to be done, maybe that's where one should look. Josef has a question.
I mean, if you think in Denef language, this is a two-center solution where one center has 16 supersymmetries, the other one has 8 supersymmetries. I don't think you can get the horizon. I don't think you can get inside the parabola with such a solution, just because, by dualities.
I'm showing you don't get inside the parabola.
Yeah, but I think in principle you can show that you can never get, if you have a two-center solution with one with 8 supercharges and one with 4, and one with 16, I don't think you can get inside. I think you
Yeah,
can also
this.
show it by
I mean, yeah, Nick was asking about much more general things, but for sure in this family, within this family, it's easy to prove you never get inside the problem. Okay, so then let me wrap up. So I've presented the first family of free-charge, asymptotically flat microstate solutions involving shockwaves. In the ADS limit, we've proposed the holographic description, and we developed this with including a precision holographic test to refine the proposal. And some brief future directions are that, as we discussed with Nick along the way, we could certainly, well, I expect we should be able to make quite a lot more general solutions involving shockwaves and use them to potentially clarify and discuss further the scrambling physics of perturbed microstate geometries. Separately, these shockwave singularities should be resolvable, not necessarily in supergravity, but perhaps in string theory, and I think Emil is going to talk a little bit about that tomorrow. And also of interest is that one may be able to use these singular solutions as some data points on the edge of the phase space of smooth microstate geometries. So perhaps we can use this to, as you know, experience tends to show that every time you make a new kind of solution, it shows you a little bit, gives you a bit more information on the next more general class. And these are, in a sort of limited way, related to the interpolating solutions that Misaki has talked about in previous examples of this conference series. So I think there's some opportunity there for some future work. So I'll leave it there. Thank you for your attention.
There's a question from Zoom by Andrea. I can ask it. I don't know if he can speak. So question for David. In the appendix of the paper with Don and Ben, we discuss shockwaves in a class of three-charge geometries. Is this a special case of your solutions?
Thank you for the question. So, okay, so the question is, what's the relation to the appendix of Andrea's paper? So I deliberately didn't include specifics on this in the out of politeness, but let me try and choose carefully some words. So Andrea's paper with Don had a nice analysis of previously existing two-charge solutions. In the appendix, they had a discussion about three-charge solutions, but those some metrics were written which were not solutions to anything. So they said one might be able to do a similar thing. They wrote down some metric and some fields, and they said, we haven't actually checked whether this is a solution. We did check, and it's not a solution. So in some sense, I'm giving you the solution. So there was a guess, yeah. So there was a guess in your appendix. We checked that the guess wasn't correct, and I'm showing you what we found as actual solutions. Yeah.
One last quick question: if you so the whole point of this sort of game is that you're making the number of these undetermined strands stringy because you made them sum up to less than n, right? There's some of the DIs being parametric less than n to the 1, and that's sort of what makes them sort of stringy as opposed to supergravity, you like.
It's what makes them not resolve. It makes their overall back reaction not resolvable in supergravity.
Perhaps how, as you crank that up, that these states were giving you a coarse-grained ensemble average in some sense over.
I would expect to actually resolve this in supergravity. I think you need to go to a slightly different class of states where you can see these kind of wiggles. So within smooth superstrata, what I would expect is you might be able to approach nearby these states. In those limits where you do allow the degeneracies to scale linearly with capital N. And then you'll get nearby, and hopefully with more wiggles, you can also go way inside the parabola as far as you like. As a separate thing, I expect there should be solutions which are superstrata containing shockwaves, actually singular shockwaves, which should be have CFT duals similar to this, where you have some component of superstratum-like strands, plus some longer shockwave strands which are not resolving. And that should be an even larger class of things which can be studied in the bulk.
Do you know the worldsheet theory for these backgrounds? And is this what you mean by string resolution?
Yeah,
or you
this
mean
is
the
what I
brain
mean.
configuration?
So we're looking into it. Well, not so. The short answer is no, not for the well. Oh, and yes, for the two charge, yes, actually. So in the two charge limit, we have a paper with Emil and Stefano from 2 years ago, where we showed how you can study the whole two charge, whole moduli space on the worldsheet. For the three charge, not yet. We don't know that, but it might be possible. And but what you can do separately, I don't want to steal Emil's thunder, but you can look at the limit of these shockwaves where there are small fluctuations and see them in the spectrum. So more on that on Friday.
In the first solution, you were talking about just the PP wave standard. It can be time dependent, as you said. Were there some attempt to have like a time dependent solution having the singularity only in an interval between two hyperplane?
Very good question. As far as I know, nobody's tried to put that time dependent shockwave in a microstate geometry. But of course, it's more difficult. But something that could be nice to try in the two charge approximation for starters. So yeah, nobody tried as far as I know.
Okay, thanks David. So let's thank the speaker again.